Welcome to Principles of Flight Section 6. Now in this section we're going to take a closer look at the cockpit placard and in particular we're going to look at G-forces, the relationship between stalling or the stalling speed and G. We're going to look at placard limits versus design limits, the manoeuvring envelope, the effects of gusts, and then we'll just touch on the safety margins that are built into the system. So first of all, let's just take a look at the placard. This placard here being displayed is a standard BGA placard, so you'll find something like this in most UK gliders, and you have the registration at the top, the type of aircraft, its category, and then a set of speed limitations followed by a set of weight limitations, and then typically it's signed and dated at the bottom there somewhere. And this is the standard flight limitations placard. Of course, when it comes to weight, and particularly in a two-seater, it becomes slightly more complex because we need to consider weight and balance and the position of the centre of gravity. So in those cases, it's not at all uncommon to find you have a placard presented to you like this for weights, and on the left-hand column on this one you'll see it says rear cockpit load in pounds, and that's the weight of the pilot in the rear seat with his parachute and any other personal equipment he's got. So if we scroll down to the 200-pound part of the rear cockpit load on the left-hand side and then read across, you can see that we've got 2 columns in the green and 2 columns in the red. So let's look at the 2 columns in the green to start with. The green section is the non-aerobatic set of limits, and you'll see that the maximum weight of the pilot in the front seat in that configuration is 217 pounds, and that will include all of his equipment. The minimum weight in that front seat is 121. So the pilot in the front seat needs to weigh between those two values, and if he's less than 121 pounds, he'll need to add ballast weight to bring himself up to that or beyond that value. And if he weighs greater than 217 pounds, he's not able to fly it with that weight of pilot in the rear seat. If we move to the red column, you'll see that you've got on the left 111, and this is the aerobatic maximum. So to fly aerobatics in this particular glider with a 200-pound pilot in the rear, you'll need a maximum of 111 in the front, but of course the minimum in the front is 121 if you look, and therefore can't be done. So you can't actually fly aerobatics in that configuration. Below the placard there, you've got the total weight of the cockpit load and its values not to exceed, and then we've got some details about the weak link, type of weak link, tyre pressures and so forth. And that's a standard format to determine the centre of gravity is in the right place in a two-seater. All of this data can be found either in the flight manual or the BGA datasheet. And the BGA datasheets can be found on the BGA website, and if you search under technical datasheets, so go onto the website, technical data sheets, and then find the particular aircraft that you're looking at. The one we have displayed here is for a K-13, and if I just expand that a little bit, you can see that we've got quite a lot of information here. Much of it you won't really need for flying, but you've got the weight data, the control deflections, so how far each of the controls is permitted to move. We've got C of G datum information, and at the bottom there we've got speeds. And if you go across to the right hand side, you can see the weighing data in more detail, and we've got maximum weight. So the maximum weight, according to the manufacturer's manual, will be 1060 pounds. So whatever, the whole aircraft shouldn't weigh more than that. Several years ago now, the BGA put a concession on UK aircraft and inflated that value by 10%, but it needed to remain non-aerobatic in that configuration, and that meant that the maximum weight was lifted up to 1166 pounds, but only applies in the UK and it doesn't apply in the rest of Europe. The maximum weight of the non-lifting parts, which is the third line down, non-lifting parts is everything really except the wings themselves, so the fuselage and its contents mustn't exceed a certain value, and that's in this case 710 pounds. What the British Gliding Association have done is uplifted that to 816 pounds is the maximum weight for non-lifting parts. And then the bottom entry is the maximum pilot weight, which is in any event, irrespective of all the weights, an individual pilot mustn't weigh more than 242 pounds. And this is fundamentally for crashworthiness reasons. The G limits, which you can find in the flight manual, and here is one for a K13. The limit load factor is 4G up and 2G down, with a safety factor of 2. So that's the limit load factor as per the flight manual. So what do we mean by G? Well, G is the load factor, the amount of weight that we're asking the glider to actually carry, and 1G represents normal gliding unaccelerated flight. And if you remember from our previous lectures, the total reaction was equal to the weight, and the total reaction is virtually the same as lift. So it's very, very close. So we could say that lift equals the total reaction, and therefore we get an equation for G from that, and that is the G is the lift divided by the weight. And if the lift divided by the weight is 1, then G is 1. You're experiencing 1G. Sometimes you'll find that the letter G isn't used, and you'll find the letter N being used instead, and then N stands for normal acceleration or load factor, and that appears in some of the data. We measure G with an accelerometer. So in the aircraft we can use an instrument like this, which has 3 needles on it. And if you look at the one on the left, you can see the 3 needles. One of them floats and just moves. The other 2 show the limits and then stick there until it's reset. So the upper needle will show the maximum G that had been given prior or since its last reset, and the lower one will give the negative G effect. And you use the little lever to push that and reset the needles all back to 1. When the needles go back to normal, it isn't 0, is actually 1, because the aircraft is in 1G, of course. If you look at the instrument on the right, you can see that the white needle is sat on 1, which would be the normal G position, and the upper needle is just beyond 3.5 G, and the lower needle is about 1.5 G. And that is showing the pilot that during that flight the G experience was 3.5 positive and 1.5 negative as a maximum, so he's operating somewhere in there. And a word of caution here is that when you land, you rumble across the ground and hit even relatively small bumps, it will jostle this instrument around and you can get some erroneous readings. So really it's only useful when you're reading it in the air. Now the relationship between the stall speed and G, if you remember this diagram from our previous lectures, you can see that wings level at 1G, the stalling speed in this example is 33 knots. And as we bank, so the G progressively increases, and so does the stalling speed. And this is highly relevant for the next slide, which I'll show you, because we can plot G and against the load factor against the airspeed, and we produce what we call the stall line, and you can see at 1G you can read off a stall speed, and the stall speed progressively increases as the speed increases, and you can see there at 80 knots or thereabouts we've got over 5G. So if we pull 5G, the glider will stall. Now the stall line shows the limit of G that we can actually apply to the airframe at any one time. So if, for instance, we were to attempt to pull 4G at 40 knots, it's not going to be possible because the aircraft will stall first before we can actually apply that load to the aircraft. So there's only a limit to the amount of G that we can pull at any one speed. And if we look at this graph now, we can see the stall line, and fundamentally there are exceptions which we'll come to later, but fundamentally it's not possible to apply the G to the left of that line because the aircraft will want to stall first. However, it is possible to the right of the line. So these are talking all about the Placard limits, and they're taken from the flight manual and often but not always displayed in the cockpit, or certainly G isn't always displayed. Design limits are something else, which we're just going to come on to now. So when we're looking at speed, for instance, the aircraft has been designed to fly at a maximum speed. It's a design dive speed, which we shouldn't obviously exceed, and we bring the placarded speed below that figure. So typically, as we have in this diagram, you've got VD, or the design dive speed, and then the never to exceed speed, which falls short of that. And the never to exceed speed is roughly 90% of VD, as we can see here. And looking at the airspeed indicator on the right hand side, you can see a green arc running around from roughly the 4 o'clock position through to almost 12 o'clock, and then that line turns into a yellow line, and then it stops where I've got my red arrow on a red line, which is VNE, and that's a very useful thing for a pilot, because he doesn't need to look at the placard to check that his speed's not exceeding VNE. He's got a visual display in front of him. So as far as the design limits for G are concerned, this is where they fall. If we were to find 5.3 G on the stall line, that point is called VA. It's the maximum design manoeuvring speed, and that's VA. And up to that speed, we can apply full control deflections on the aircraft without too much worry, because should the aircraft stall, it will should we apply too much G, we can't apply more than 5.3, which is the design limit. At 4G, the design limit for G is actually at VD is 4G, and that means that the limit load line, as we've got here, runs from 5.3 down to 4G. So it's a sloping line there. And these standards, I've taken this one from a K13 diagram and adjusted it, because the design standards over the years have changed, and you will find some gliders, like the older K13s, had slightly different design standards when they were produced. So the K13 was under the OSTIV. Later came JAR22, and today aircraft are designed to CS22, and that's just a set of standards. The difference between them, as far as we're concerned, is negligible, and so for our purposes, we're going to be talking in terms of CS22, which is the modern one. The difference between a design limit and a placard limit we'll show here. The design limits, or the placard limits, are always less than the design limits, and that's to give us some margin of safety. So in terms of speed, we won't go up to the design limit, we'll go to something different, and as far as G is concerned, the same. So we'll give ourselves a margin in all directions. We can now see the beginnings of a manoeuvring envelope, because if we're looking at G on the left hand side and speed, the airspeed on the horizontal axis, and we've got the stall line, the limit load line, which goes from 5.3 down to 4, and the design dive speed, VD, which is the vertical line on the right hand side. And you can see that the manoeuvring envelope also covers negative loads as well. And that whole setup is called a manoeuvring envelope. Now, the effect of gusts. If we hit a gust, then the angle of attack increases, and because the angle of attack increases, the coefficient of lift increases, and therefore the G loading increases. So in other words, we meet a gust, the G loading is increased, and that has an important significance here. Is when we look at the flight envelope, if we happen to be manoeuvring and perhaps in a situation where we're perhaps pulling 2.5 G during a manoeuvre, like a loop perhaps, and then we meet a gust which is another 2 G, then we can see that very quickly we're getting up to, like in this case, 4G or 4.5 G, and we could take us beyond the limits of the aircraft. So gusts are a very important element, and we wouldn't be pulling high G values in gusty conditions, basically because the effect of a gust will take the glider closer to its limits. We can now look at the safety margins involved. Now on the left hand of these two graphs you can see a flight or manoeuvring envelope, and instead of VA and VD, what I've put on here is N1 and N2. N1 being at 5.3 G on the stall line, and N2, or normal acceleration, being on the design limit line at 4G. And the line between those two is called a limit load line. Now beyond that line we have an additional 50% of spare capacity, if you like, because at the limit load line the aircraft will certainly be damaged if you go beyond that, and it won't be a very good situation, but it won't fall apart yet. The ultimate load line is higher up, as you can see on the right hand side, and then now you've got trouble with the capital T, because things are going to start falling off the aircraft because you've gone beyond too far beyond the limit load line. In either case, the aircraft, if you've taken the aircraft beyond the limit load line, you're going to have to get the aircraft inspected, and it's going to be a big deal. So, however, as we can see here, if we look at the safety margins for airspeed, the margins here are actually relatively small. So unlike the 50% uplift we've got on G, here we've only got 10%. So VNE represents about 90% of VD, the demonstrated, and the demonstrated flight diving speed is a flight that the test pilots taken the glider to. So he won't go to VD, he'll go somewhere beyond VNE to check that the aircraft behaves the way it should, but he won't take it up to VD. So we now have, if you like, a number of measures for airspeed. We have VD, the designed maximum dive speed, VDF, which is a demonstrated flight, so that's done under test conditions, and then VNE, which is your placard. And the difference between your placard and the design limit is just 10%. So summarising the speeds, VA is the maximum manoeuvre speed, VNE is the never to exceed speed, VDF is a demonstrated flight speed, and VD is the design dive speed. So we need to refer to the flight manual for operating G limits, but if you use CS22 then it's 5.3 G at VA and 4 G at VD. And older aircraft may have slightly different standards, so OSTIV and JRR might be different. But an important point to note with the G and the speed limitations is if you're put in that horrible position of having to choose, do I pull back on the stick to reduce, to control the speed, or do I just let the speed go too fast? And don't go beyond VNE if you have to pull too much G. It's not a good situation either way around, but your safety margins are much better in the G direction than they are in the speed direction. So that's it for this one. We've looked at the cockpit placard, we've looked at G forces, we've looked at the relationship between stalling, the stalling speed and the G, and we've looked at placard limits versus design limits. We've looked at the manoeuvring envelope, which we'll come back to again in a later lecture. We've looked at the effects of gusts on that, and we've looked at safety margins. I hope you found that helpful, and I'll see you next time. Bye for now.